recording going? Okay, good. Now, first things first, I will be doing my classes at least for the next 1 or 2 weeks online, and the recordings are available. I'll make them available on YouTube sooner than later, typically within a day or so. Now, about the quiz on Thursday, I'm trying to make an arrangement for in-class quiz so that one faculty member or TA can come in and administer the quiz on my behalf. And then I will continue and take over the lecture and continue after the quiz has been done. So that's the plan for now. Either ways, I'll keep you posted. You'll have enough information. So for now, you should assume that there is going to be an in-class quiz on Thursday, the day after tomorrow. And then I'll keep you posted about that. Okay. Now, let's see what we did in the last class. We started with delays, right? So I know it's a little bit uncomfortable to unmute your mic, and then I also tend to impose on you by calling out on you or waiting for a volunteer to respond. I know it's not very comfortable, but I think it is very important for keeping our attention and focus in the class if we make it a discussion session, rather than me talking all the way through. So I rely on your help in making this class a discussion session, and I would very much appreciate, and this applies to the class, the whole of the class today and the rest of the semester as well. So you continue to take more and more initiative in asking questions, in volunteering to discuss, so on and so forth. So with that said, let's see, 3 p.m. section, continue. So what did we do in the last class? Can I have some volunteers to review 1 or 2 points that we did in the last class?
Yeah, Professor, this is Jeff. So one thing we talked about was estimating delays using the Elmore estimation for RC ladders.
Correct. We looked at Elmore delay estimation for RC ladders. So if there is a bunch of resistors, like so, and each of these nodes has a capacitance, Cn, okay? If each of these, and the signal source is over here, okay? Elmore delay states that the total delay can be expressed in terms of I, where I is the resistance from node I. So this is nodes, which goes from 0 all the way through n. Ri to source. So the total resistance in the path at that node all the way to the signal source times the capacitance at that node. Okay, so we saw that this equates to, this comes to R1 C1 plus R1 plus R2 times C2 plus so on, plus R1 plus R2 times Cn. Okay, we used excuse me, we used this Elmore delay method to calculate the rise time and fall time. One of these for a 3-input NAND gate. I think it was the fall time that we calculated using the Elmore delay for the NAND gate. What else? What else did we do? Go through your notes and remind us as a class in terms of what we did in the last class.
Did we learn about TPD rising and TPD falling?
TPD rising, TPD falling, sure. And we saw how to calculate the KP and KN values for any gate, logic gate. Okay, so we did a bunch of examples. If I give a 2-input NOR gate and I ask you to find the delay, we know how to pick the value of KP and how to pick a value for KN. Okay, the KN value here is going to be 1 because we choose for the worst case. Whenever there is a parallel path, there are 2 scenarios possible, best case and worst case. Okay, now for the 2 NMOS in series, in parallel, the worst case happens that one of the parallel paths is off and only one is on. So because nothing is specified, I'm trying to make the resistance in the pull down network equals to 1R. K R over Kn, that's the resistance of this NMOS over here. And I'm trying to make that equal 1R. Okay, and from there, I can get a value of Kn equals to 1. And similarly, I can get a value of Kp equals to, what would be the value for Kp over here?
Would it be 4?
4 is the right answer, because for a PMOS transistor, the resistance is 2R over Kp, and I'm going to try to make it equal R. So, or if I leave Kp as unknown, okay, and I have 2 of those in series here, 2R over Kp. So the total series equivalent should be R, giving a value of Kp equals to 4. So we saw that. Once we have the values of Kp and Kn, we know how to substitute how to estimate the capacitances on these nodes. Okay, the capacitances on these nodes are going to be 1C coming from the NMOS here, 1C coming from the NMOS here, and then 4C cap coming from the PMOS over here. Okay, so at the output node, we know the total capacitance is going to be 6C from the parasitics or the driver. And then we have to look into the load as well. So in this context, I mentioned something like this. Let's take an example of a NAND gate. Okay, let's take the example of a NAND gate that looks like so. I think I got away by underestimating the capacitance. Okay, so we can pick a value of K and Kp equals to 2 over here. So 2. I'll pick a value of Kn equals to 2 as well. So I'm going to pick a value of 2 here. So what I got away with in the last class was pertinent to this node. Okay, something about that node. What I did exactly was I mentioned that I can simply estimate it to be 2C capacitance. And I kind of ignored the 2C capacitance here. And I said, I can do a simplification that I can do a implementation that reduces 2C. So my question is, what do you think can be done in order to reduce the capacitance here from 4C to 2C? Okay, so normally I would expect a capacitance from the source of this guy and another capacitance from the drain of this guy. Okay, so I would expect a total capacitance of 4C over there. Okay, this is a really neat technique. The idea is this. Okay, let's say I have two NMOS transistors fabricated like this. Okay, let me call this transistor M1. So that is this guy M1. The drain of this guy is shown here. The source is shown here. Okay, for the next transistor, for transistor M2, that is laid out next to the NMOS to M1. Okay, that's the gate 2. Okay, so this happens to be the drain of second NMOS, drain 2, and this happens to be source 1. Okay, this is drain 2, source 2. Source 2 is connected to ground. Okay, drain 1 is connected to the output node. Okay, let me draw that here. Okay, that's drain 2. Now this connection between source 1 to drain 2, that is made using a metal contact, using a metal wire. Okay, that represents the blue dot over here, the purple dot over here. Okay, now the idea behind being able to reduce this capacitance is, so we know each of these diffusion regions produce a capacitance, right? Kn times, so this drain produces a capacitance of 2C. The source produces a capacitance of 2C, and this is transistor M2, by the way. So the drain produces a capacitance of 2C, and the source produces a cap of 2C. Now, the argument that I'm making is based on the fact that this node here, the node here, the intermediate node, this guy, has no external connections. So what I'm going to do is a simplified implementation. I'm going to leave the drain 1 like so. I'm going to combine the source of 1 and the drain of 2 into one big diffusion region. Okay, I don't necessarily say one big diffusion region, but I'll say one into one entity. Okay, and I don't explicitly connect using a metal wire, blue wire. So here is transistor M1, here is transistor M2. So we know each of these diffusion regions produces a capacitance of Kp times C. Okay, therefore it's going to be 2C as well, and this is 2C as well. So if I assume that I can combine the source and drain regions, and that is possible only at this node because there is no external connections. So when I can non-contacted, so this is called non-contacted or uncontacted intermediate node. So the capacitance at this uncontacted intermediate node, if it is uncontacted, we can get a value of 2C. And that's the understanding that I have used to, oops, that's the understanding or simplification I have used to estimate the capacitance on this node to be 2C as opposed to being 4C. Okay. The same applies over here as well. If they're contacted, there is going to be a capacitance of 8C. If they are not contacted, there is just going to be a capacitance of 4C. All right. Questions about that, please? Okay. So that's one of the things that we did. What else did we do in the last class? We looked at the linear delay model. D is F plus P. Diane is a friendly person. And by friendly, we mean she gives out great hugs. So this is the delay model that we looked at. Delay equals to GH plus P, very similar to Y equals to MX plus C is a straight line. Okay, and delay, and this is something I have not mentioned, is in units of tau, which is equals to 3RC. Okay, I have a question for you. Go back to your notes on inverter. Okay, and then we looked at the delay of inverter at that node. Okay, we looked at the delay of that inverter at this node. So unit inverter with fan out 1. Okay, so if you go back to this, if I call 3RC equals to tau, okay, what is the total value of the delay? And we saw that TPD and TPD rising and TPD falling were equal in this case. If you go back and see, you will notice that this is 2 times of tau, okay, where tau is 1 times RC, okay, tau plus tau, okay. So this is called the load component, and this is called the parasitic. Okay, this is also called the driver. Okay, and load is also called parasitic free load. So when I say something is, give me the parasitic free delay for a fan out 1, I am referring to the load component of it. If I say, give me the delay of a load free, it's not often that we drive no load, but if I were to say, give me the value of a delay that is of an inverter that is load free, what I mean is I'm talking about just this component, okay, load free. Real circuits have load and real circuits have parasitics. This component is called the load free component, and this component is called the parasitic free component. Okay, so that's something we want to understand. Everything in units of tau, where tau is 1 times RC. Okay, tau is 3 times RC. Sorry, tau is 3 times RC. So I want to go back to my point. The idea is we looked at delay. All of these equations are in terms of 3 RC. Okay, so let's continue that. We will hopefully be able to finish our discussion. So I defined a few terms. I defined what D is. D is the delay. F is the effort component. G is the logical effort. And H is the electrical delay, so on and so forth. I defined all these terms. Okay, and then we looked at the definitions for fan out. We started looking at the definition for fan out. This is the number of identical loads. Okay, and if the load, that's the value H. If the number of identical loads is not clear, if it's not driving identical loads, or under more complicated scenarios where I cannot give you the number of identical nodes, the definition of fan out can be written out as C out over C in. And this is also called electrical effort. Okay, the overall output capacitance over the overall input capacitance. And then I talked about G, logical effort. Okay, let me give you a question that is a favorite topic for interviewers. Okay, the question is, for a NAND gate or NOR gate can be used as universal gates. Okay, you can implement almost any logic or just about any combinational logic using NAND gate and NOR gate. Okay, now if you want to implement an inverter using this guy, all you do is you simply tie the inputs to. So in other words, the idea is you can implement any gate using NAND logic or NOR logic. So the question is, which one do you prefer? Which one would you prefer? So in other words, let's say a simple inverter implemented out of a NAND gate looks like this, and a simple inverter implemented out of a NOR gate looks like this. Both the inputs are tied, 2 input NAND gates, 2 input NOR gates. So this is A times A whole complement, which is A complement if the input is A. Now this is A plus A whole complement, which is A complement. So the input is A, the output is A naught. So this NAND gate is configured to be an inverter. This NOR gate is configured to be inverter. The question is, which one is better?
The simpler design, so NAND gate.
NAND gate is better, and why would you think so?
Because you just send in two of the same signals, I guess.
Send
That's my
both
logic.
input signals.
Yeah.
So you can, that is correct. The NAND logic is faster than NOR logic for a very specific reason, which is rooted in a Cmos implementation. If you look at the Cmos logic implementation of a NAND gate, that looks like so. PMOS transistors are in parallel, and NMOS transistor is in series. Okay, so this is NAND logic. Where the NMOS in series, the NOR logic is the complement of that. The PMOS transistors are in series and NMOS are in parallel. So this is NOR. Here, if you pay attention, the PMOS are in series. So the idea is NAND logic has faster NMOS in series, while NOR logic has slower PMOS in series. So the worst case is the series combination, or in other words, the series combination of NMOS is going to suffer less compared to series combination of PMOS. So we prefer the logic which has faster NMOS in series. So in general, that is NAND logic. And if you think about it, that is going to bear out. This logical argument is going to bear out when you calculate the G, or the logical effort. Okay, when you calculate the logical effort of NAND gate and NOR gate. Okay, let's quickly do the logical effort of a NAND gate and NOR gate. Let's first define what it is. Okay, so G, which is the logical effort, is defined as C in of a gate to the over C in of an inverter. Okay, C in of an inverter. So let's try to do we did this. Let's try to do the logical effort for the inverter. Okay, when we do the logical effort for the inverter, this is A and this is output Y. And then I pick a value of Kp equals to 2 and K in equals to 1. Okay, what is C in for this guy? C in. So that's the total capacitance connected to the input side. Okay, the total capacitance connected to the input side is there is a capacitance of 2C over here, and there's a capacitance of C over here. So the total C in is going to be 3C, and C in over C in of an inverter, that is equals to 3C. So in other words, the logical effort for an inverter is 1. Okay, because we are dividing by its own input capacitance. Okay, let's let's use this definition. Okay, to evaluate the C in for NAND gate and NOR gate. So what I want you to do is I want you to evaluate the G in for both of these circuits. And then I'll pick one of you to answer that question. Okay, I'll pick one of you to answer this question. What information would you need from me? Okay, here is a NOR gate. The information that you would need from me is the values of Kp and Kn. You might as well calculate them. Let's say I give you a value of 2 for Kp, okay? And I give you a value of 4 for this Kp over here. And I give you a value of 2 for Kn and a value of 1 for Kn over here. The output is over there. What you want to remember is that when we are calculating the input capacitance, we are looking at the capacitance on each of these nodes, okay? Each of these nodes, I know. So one input is B and another input is A. So what is the capacitance looking into one input? So I would have to find the capacitance at the gate of the PMOS and down below at the gate of the NMOS, okay? So C in of the gate, in this case, the gate is a Nand gate. What is this value? And what is this value over here? I know the other term, C in of the inverter, right? That is 3C, and that C in of the inverter is 3C as well, okay? So the G, or the logical effort for NAND gate, can be calculated if we know the C in over there. Similarly, G of the NOR gate can be calculated if I know the numerator, okay? All right, let's see, any volunteers to answer that question? Let's pick, Ankita, can you help us? If not, you could pick somebody else.
Is it 3C?
3C, which one? The one on the left or the right? So on the right, there is
The one on the
capacitance.
left.
The one on the left, there is a cap of 2C over here, followed by, there is a cap of, remember, Kn equals to 2. So the capacitance is going to be C times Kn, which is C times 2. Okay, so for NMOS transistor and PMOS transistor, all the capacitances, capacitance in the drain, capacitance in the gate, capacitance in the source, are approximated to be Kn times C for NMOS, or Kp times C. So for the PMOS transistor, there is a value of Kp equals to 2 over here. So the capacitance on the gate, C gate, or the input for the PMOS transistor is 2C. Capacitance on the gate of the NMOS transistor is Kn times 2C. So that will be a value of 4C in total, right? 2C in parallel with 2C. Okay, how about this guy? How about the one on the right?
5C?
5C, it will be a capacitance of, let's see, this is 4C over here, and this is 1C over here. So the total capacitance is 5C. So if you simplify, NAND gate has a logical effort of 4/3, while the NOR gate has a logical effort of 5/3. And that's exactly the conclusion we arrived at. NAND is better. NAND is better, right? That's exactly what we discussed here, saying NAND has faster PMOS and MOS transistor. Therefore, NAND is the right answer for minimizing delay. So that is shown in terms of the logical effort here. NAND has lower logical effort compared to NOR. Okay, questions, please.
Does the mobility of holes also play an effect here, or no?
Yes, yes. The mobility of holes is in effect. If you think about it, two NMOSs in series only incur a Kn value of 2. But two PMOS in series need a Kp value of 4, because to sustain the same current, because the mobility of holes is slower, we need to have wider PMOS compared to the NMOS. Okay, wider PMOS means larger capacitance. Okay, that's exactly the reason. The mobility of holes is slower, so the resulting current is slower. So in order to compensate for that, I use a wider PMOS transistor by picking a value of Kp equals to 4. Okay, remember Kp and Kn values. Remember they represent the aspect ratio or the width over length. Okay, that's a very good question. That's a good observation. Other questions, please. Okay. Now, we already discussed about tau, which is CRC, right? For an inverter with a fan out of 1, an inverter with a fan out of 1, the total capacitance, or the total delay.
Wait, one question.
Yes.
On the previous problem, why did we only look at one set of gates?
Why did we look at only one set of gates? That's a very good question. Thank you. If I am looking at a NAND gate with 2 inputs that is being driven by another NAND gate, okay? So at that node, this is the parasitic or the driver. The load is only looking into one of the inputs. I don't connect them to both the inputs. So this is, when I calculate the delay at this node, that is only being, that's only driving one of the inputs of the, so the input, they're connected independently. Okay, this is driven by a different driver, and this is driven by a different driver. So there are two independent, different entities, different terminals. Does that make sense? Okay. If it doesn't, feel free to probe further. Okay, so that's a very good question. So it turns out this parasitic delay tau is also called a parasitic delay. And then we looked at the different manifestations of it: parasitic free load delay, load free parasitic delay, so on and so forth. Okay. Now, let's do a quick problem here. Let's see if we can do a quick problem. I give you a bunch of, a chain of inverters that look like this. Okay. So N inverters. So this is the idea of the ring oscillator, right? So for your first project, you're supposed to do a ring oscillator, implement a ring oscillator. So let's say I give you the values here. I give you the value of G, logical effort. We know the value of a logical effort for a unit inverter. Okay, for the unit inverter, it will not be the same for a different inverter. Cn over Cin of an inverter. I should clearly say this is a unit inverter. If the numerator is also a unit inverter, then I'll get a value of G equals to 1. If not, I have to carefully evaluate the numerator and denominator separately. The denominator is 3C. Okay, and then I have to carefully see what the value of the capacitance is in the numerator for an inverter. So for a unit inverter, the G value is given to be 1. What is the load or what is the fan out in this case? At each of these nodes,
Isn't it
what is the
N?
fan?
Isn't it? Because we don't know exactly how many there are, right? Or is it just one?
1 is the right answer. At each of these nodes, we don't know. That's exactly true. We don't know the total number of inverters in here. It's just given to be N. But we know the fan out at one node, at each of these nodes. At each of these nodes, the fan out is 1. The number of identical transistors that are being driven. Okay, and I give you the value of P, okay, to be 1. Okay, let me define P to be this. Okay, P equals to diffusion cap over the gate cap. Okay, simply saying, if I have a NMOS transistor over here and a Kn value equals to, doesn't matter, 5, some arbitrary number, then the capacitance in the drain is going to be 5C, the capacitance in the source is going to be 5C, and the capacitance in the gate is going to be 5C. So if you pick any of the diffusion value, one of these, either of the drain or source can be picked. So for this particular NMOS, the diffusion capacitance is 5C, and the gate capacitance is also 5C. So P is going to be 1 in this case. So given this, what I want you to do is to find out frequency of oscillation. Okay, you looked at ring oscillator. Let me show you how this functions. Okay, let me show you using this guy. Let's say the initial value is 1 over here. That is inverted to be a 0, which further becomes a 1, which becomes a 0. Okay, now if the n is odd, okay, if the n is odd, so like in this case, I'm highlighting the outputs of the transistors for which the n is odd. Okay, that's this guy, that's this guy. Okay, odd. If n is odd, the input 1 is inverted at the output. So assuming the overall number of n is odd, I can expect a 0 here after some delay. Let's say there is a delay of d in each of these nodes. Okay, then what happens is all of these delays get added. So once I make this input 1, and after it passes through each of these delay stages, it has to become a 0. Okay, now this 0 passes through each of these stages and next becomes a 1. So this circuit overall keeps oscillating between 0 and 1. So the question is, if it is oscillating, what is the frequency of oscillation? Can we know that? Okay, so I input 1, okay, that's the initial input. After a delay of d, that becomes a 0. Okay, now after a further delay of d, this 0 becomes a 1. Okay, now after a further delay of d, this 1 becomes a 0 because it's oscillating between 1 and 0. A further delay of d, it will be 0, and then it'll oscillate back to, raise back to 1. So this node is oscillating between 1 and 0. And if you look at the output node, which is this guy, that guy is oscillating between 0 and 1. Okay? That guy is oscillating between 0 and 1. Okay? Now, as a matter of fact, both of these nodes are the same. Okay? They're the same node. Sorry about that. So they're the same node oscillating between 0 and 1. Now the delay, I should be able to find the frequency of operation of this, frequency of oscillation of this wave, right? What would be the frequency of oscillation? N times D, okay? N times D, N times D. Because the delay at one node is D. If it passes through, the time it takes to pass through each of these delays is N times D, okay? So the frequency of oscillation is 1 over the clock period, which is this guy, okay? Which is 2 times N times D, okay? So the frequency of oscillation is going to be 1 over 2 times N times delay is G times H plus P. This is the linear delay model, remember? So we know the value of G to be 1. We know the value of H to be 1 because that's the fan out. And we know the value of P to be 1, 5C over 5C. So if I plug that in, F is going to be 1 over 2N times G times H plus P. So this is going to be 1 over 4N, where N is the number of stages. And it's odd. Questions, please.
Where did the 2 come from?
Where did the 2 come from? Good. If you look at this wave, this is actually 2 times ND. Okay. If you look at this wave, this is 1 ND and this is 1 ND. If I'm measuring the clock period from one rising edge to another rising edge, so that is 2 times ND. Okay. I should have, thank you for catching that. It's 2 ND. Does that make sense? That's the total time period. Okay, 2 times ND, 1 over time period is the frequency of operation.
So just to clarify, it's always 2 ND?
It's always 2 times ND, correct? Because it's going to be, the reason if you think about it is, the one is going to be, the one at the very end, very left end is going to be stable for a time period of N times D. Then it changes back to 0, which will remain for N times D. So if you look at a full cycle of 1 and 0, then the total is going to be 2 times ND. Yes, it's always going to be 2 times ND because that's one full cycle.
Question, does this always generate the 50% duty cycle?
Yes, it typically generates 50% duty cycle. It doesn't discriminate between 0 and 1.
Okay, great, thanks.
Yes, please. Other questions? Okay, and then it so happens here the duty cycle is 50% perfectly because TPD rise time is the same as TPD fall time for an inverter. Remember, it was 6 times RC, or in that order, sometime in something in that range. Okay, the rise time is equals to the fall time. Therefore, the duty cycle is going to be, the delays are going to be matched. Okay, let's do another simple problem. And this is, I think, more or less we have solved this problem in some sense earlier. There is an inverter here, and it's driving 4 identical loads. Okay. It's driving 4 identical loads. Okay. What would be the delay at that node? What's the delay at this node? Using the values that I have already given you, I want the answer in terms of tau.
Wouldn't it be tau plus 4 tau?
Tau plus 4 tau, 5 tau, or 5, right? Because all of these values are expressed in terms of tau. So it's going to be 1 tau plus 4 tau. So if you think about it, the G value is 1, the H value is 4, the P value is 1. So delay is going to be 4 plus 1, and this is all in units of tau. Okay, so the delay is going to be 5 in terms of tau. So we simply use this GH plus P linear model. It's a very straightforward application of the GH plus P model. Okay. All right. What I will quickly give you is, let's say I have a bunch of paths. Okay. We have so far only looked at one circuit driving a bunch of other identical loads. Okay. What if I have more than that? What if I have a path? When you're designing a circuit, you want to know how much delay you are going to incur along a path. Or do I increase the number of stages, or do I decrease the number of stages? So on and so forth. Okay. It can be expressed. F is logical effort. It can be expressed in terms of capital G times B times H. Okay, these are all parameters. The logical effort, the electrical effort, so on and so forth for the path. We know how to calculate this H, right? C out over C in. So I'll not get into the details of this. It's all related to paths. The idea is, and B is the branching effort, by the way. This is the only one that I did not define, branching effort. So without getting into the details of this, I'll give you a key conclusion. It looks like this. The delay of a path is a function of the number of stages in the path. Okay. As you increase the number of stages, in this case, 1, 2, 3, 4, there are 4 stages, the delay increases as well. Times 1 over f to the power of 1 over n plus p. Okay. So this is the minimum delay. minimum delay happens when I pick a value of n that satisfies that satisfies this expression. Okay, that's the minimum delay possible. So we leave the discussion on delays with this and then move on to talking about power. Okay, any questions, please? Questions before we move on to power and we leave the topic of delay. Okay. All right, let's talk about power now then. Okay, these are two sides of the same coin. If you increase power supply, the currents are all going to increase and the delay goes down. Okay, and if you reduce the power, supply, the delay is going to increase because the charging and discharging currents are small. Okay, so these are two sides of the same coin. What we typically do is PDP. We don't maximize or we don't minimize the power consumption, because minimizing the power consumption in isolation could lead a pretty badly delayed circuit. Okay, or we don't minimize the delay either. If we minimize the delay, that could be very power hungry. Okay, so what we do is we take the power delay product, and then this is one organic entity, one organic quantity that can be maximized or minimized, so that you're not doing power and delay optimizations in isolation, but this is one entity that takes care of both power and delay. So let's look at power energy. There are different kinds of power. Power consumed in CMOS is of two types. Okay, there is the static power and there is a dynamic power. Okay, the dynamic power component is happening because of switching. Okay, let's say I have an inverter that is driving a capacitance 0 to 1 to 0 to 1 to 0. Let's say there is a capacitance that is changing this output load capacitance. There's an inverter. The amount of power consumed to charge this capacitance, discharge this, and the amount of power consumed by the inverter in this process, that's the dynamic. When the inverter is doing some action, okay, even when the inverter is not doing any action, CMOS circuits typically have a small static component as well. Okay, CMOS circuits have a small static component coming mostly from leakages. Okay, so CMOS power consumption has two parts, the dynamic part and the static part. Okay, and we know the expressions for instantaneous power. It's the current times the voltage. The energy is the integral of the power over some time. And then the average power can be expressed in terms of integral 0 to t, p of t dt over the time period. Okay, so we can look at the expressions for average instantaneous power. Okay, and then there are different kinds of circuit elements. The amount of power that a source delivers, I times V, the amount of power dissipated in a resistance, okay, I square times R, and there are different V square over R, and the amount of power consumed or dissipated by stored in a capacitance, okay. is half, energy stored in a capacitance is half CV squared. Okay, and this is a very familiar form of energy for us. There is a half kx squared, half mv squared. Okay, the kinetic energy of a body moving with a velocity v, and that has a mass m. That's the kinetic energy. This is the amount of energy stored in a spring with a spring constant of k, and spring that has been um, stretched by a distance of x, so on and so forth, or compressed by a distance of x. So this half times a constant times something squared, c v squared. This is the energy stored in a capacitance. Okay, so this is a very familiar form. We will use these terms later on in the discussion. Okay, now therefore, charging a capacitance, like I mentioned earlier, if I am charging a capacitance, what typically happens is when the gate output rises, the amount of energy that is stored in the capacitance is 1/2 CL VDD squared, right? The familiar form. But what is the total energy drawn from the supply? Okay, so that is VDD times IT. So if I do the integral, I'll end up seeing that an amount of CL times VDD squared. That's the energy drawn from the source. Okay, and half of that energy is stored in the CL capacitance. What happens to the rest? The rest of the energy that is drawn in this process is dissipated in the PMOS. Okay, so a big chunk of the power that we consume, or the energy that we consume, half of it is actually consumed by the PMOS, and the rest is stored in the CMOS, in this capacitance during the charging phase. During the charging phase, the CL VDD squared amount of energy is dissipated in the PMOS, and the other half is saved in the capacitance here. Now, when we discharge it, all of this charge is dumped to the ground, okay, through the NMOS. So some of that energy stored in the capacitor is dumped to ground during the discharging phase, and part of it is dissipated as heat in the NMOS transistor. So there are two phases. When the PMOS is active, there is a charging phase that consumes 1/2 CL VDD squared of energy, and the same amount of energy is stored in the capacitance. And during the discharge phase, that energy is dumped to ground, and part of it is dissipated as the heat in the NMOS transistor. Okay, so this is the amount of energy consumed in charging a capacitance of CL. Okay. Now these are switching waveforms. On the top is the input. When the input goes from 1 to 0, the output slews its way, slowly follows more or less a square form in that sense. Okay. Now, if you look at these waveforms right here, this is the current in the PMOS transistor IP. Okay. When the current in the PMOS transistor is high, look at the corresponding current in the NMOS transistor. It's almost 0. So when this transistor is on, the NMOS transistor is off. Okay, and eventually when the PMOS turns off, the NMOS turns on. Okay, so that's the idea, except at this guy. Okay, at that instant of time, both NMOS Okay, at that instant of time, both the NMOS and PMOS are on, and that leads to a short circuit current. Okay, and then you can look at the energy and the power consumed by the PMOS, the power in the NMOS, the overall power, so on and so forth, the overall current and the overall power. Okay, but what is important to remember is that there's a teeny tiny blip for a short duration of the input when both the PMOS and the NMOS are on and they consume power. Okay, they short circuit the VDD to ground. Okay, now we can look at the power consumption, the switching power. Okay, the power switching is defined as 1 over T integral 0 to T IT times VDD dt. Okay, and we can see that the power consumed, and this is an important relationship, power consumed is C VDD squared times F switching. Okay, let F clock be the frequency of clock, and let's say my my transistor is, my inverter is not switching for all the clocks, it's only switching for a fewer number of clocks. Okay, let's say alpha F switching. Okay, okay, it's only switching. The idea is that there is a master clock with a frequency of F clock, and then on each of the rising transitions here, okay, the NMOS or the inverter does not switch. The inverter is configured to switch only on every alternate of the clocks. So in other words, the switching frequency here is 1/2, the switching frequency is 1/2 of the clock frequency. Okay, so if we take that into account, so all I have done is I have replaced the F switching with the term alpha times F clock. Okay, the alpha I mentioned is the switching activity factor. Alpha is the activity factor. Okay, so if let's say this is the master clock and F switching, and switching happens only on alternate then F switching is 1/2 of F clock. Okay, so the idea is the total power in the switching, the total power consumed for switching is alpha times C VDD squared times F. As you can clearly see, reducing the power supply has a quadratic effect in reducing the switching, in reducing the power consumption. Okay, and this is often, that's the reason why if the voltages, the power supplies constantly kept falling down. Okay, so the power supplies have over the years, okay, come down significantly because one of the reasons is that it reduces the switching power consumption. So for circuits with a very low power budget, operating at a lower power supply is one way to control the total power consumption. Okay, and then I talked about the short circuit current. the small teeny tiny blip of the current that happens when both PMOS and NMOS are on, and it's usually a small component, less than 10% of the dynamic power. Okay, and then like I mentioned, the total power consumption is the dynamic power plus the static power. Okay, the dynamic power includes the switching power, which is alpha C VDD squared times F clock. So that's this guy times the teeny tiny blip of short circuit current. Okay. Now, if you look at the static power is not coming because of charging or discharging of a capacitance. The circuit is not doing anything at all. When the circuit is not doing any charging or discharging, even then there is some kind of leakage currents. There is always a subthreshold leakage. There is the gate leakage, junction leakage, and then contention current. We will look at contention current when we look at circuit families. Pseudo, ratioed logic. Okay, so this is different from CMOS logic. So in CMOS, we found that the number of PMOS transistors is equals to the number of NMOS transistors. Okay, and then a few other features. Okay, there's conduction complement, so on and so forth. But we are going to look at different circuit families. Okay, but now the total power is the sum of the power done in order to charge and discharge the capacitance and to overcome the static power, short circuit current, and it also includes the static power, which is mostly the leakage currents. Okay? Questions, please. Questions, please. Questions, comments, concerns. What we will do is we will come back on Thursday to look at some of these simple problems. Okay, these are typical problems. The idea is, if you look at this, this is a 1 billion transistors chip with 1 billion transistors. The number of transistors that are performing logic is 50 million. The number of transistors that are implementing memory or storing is 950 million. Okay, but what is important is pay attention to this number. The activity factor is 0.1, meaning the logic gates are switching much faster compared to the activity factor of the memory. Memory, the contents of memory are not changing as frequently as the logic gates change their values. Okay, so we will find out that if you do the math, just because of the difference in this activity factor, a small number of logic components and a large number of memory components, both of those actually contribute more or less same power consumption. Okay, the logic components consume 27, they have a capacitance of 27 nanofarads, while the memory components have a capacitance of 171 nanofarads. So that is going into, that is multiplied alpha times C logic plus this alpha, which is 0.02 times 171 nano. Okay, 27 nano. This is, so we will see that it turns out that both the logic components and the memory components contribute approximately same orders of magnitude power consumption. Okay, so with that, I will stop the discussion. Any questions, please? Okay, I will find a way to have an online, a in-class quiz on Thursday. Once I have more news about that, I will let you know. But for now, assume there is going to be an in-class quiz. Okay, I'll see you folks back on Thursday.